Hi there, in this video I'm going to recap some of the stuff we've done in the first course, which was called Design a Floating Point Unit 1, Numbers. So I'm assuming that you've either covered that numbers course and you know all about floating point numbers, or you've already done floating point numbers and you've got some inclination or some idea of what's happening. So if you know nothing about floating point numbers whatsoever, you can always start the course and continue with the course and then learn as you go. But I am working under the assumption that you have some sort of knowledge of floating point numbers. So let's have a quick recap here. So if you go into the resources section, there's a tool here, an Excel spreadsheet, and if you can open it up in the tools bar here, you'll see these options. Now not all of them are actually available at the moment. I am working on them continually, but the one we're interested here is this decimal to binary to decimal annotated. So if we click on this top one here, now this gives us a floating point binary to decimal converter. So you'll have seen this in the first course if you've already done the first course, but I was just going to work through a couple of conversions just as a reminder, so you can, if you're a bit sticky on it, you can remind yourself how to use the tool and how to do the conversion. So as it says, it's converting from binary to decimal. So this is the 32-bit floating point number here. So there's 32 bits here, 1 to 32. And whenever we convert it, it goes into this box here, and this is the decimal box. So for example, if I put a value in here, then you can see that this is the value of 2. So the floating point binary is this value here, and the equivalent decimal is this value here. And I've got a copy of this value down the bottom, and I've also got stuff in between here that shows us how we were able to go from this 32-bit binary number to this decimal number. So let's remind ourselves how we went from this number to this number here. Well, you'll see that I've split the 32 bits into 3 different colour groups. The first one is the yellow. Now the first one is a sign bit, and it's really quite straightforward. If the first bit is a 0, then the sign is a positive. If the first bit is a 1, you'll see that the sign is a negative. So it just simply changes the sign of the number. Nothing else changes. So in order to change the sign, you simply change the value of the first bit. Now you can see down the bottom here, we've got the result is equal to, and in the first bracket here, this is the value of our sign. So for example, if I was to make this a value of 0, then it's going to be 1 times all of this. So we're going to get a positive number. But if I make this a 1, you'll see that then it goes to -1. So we'll have -1 times all of this is going to give us a minus number. So the first part of the result is just given by this multiplication by either -1 or +1, and that's given by the very first bit here. So that's quite straightforward. Now let's look at the next section here. So the next section here is going to have 8 bits, and this is called the exponent. Now remember, an exponent is a number, say for example 2 to the power of 2, or 2 to the power of 3, or 2 to the power of 4. So the 2, 3 and 4 are the powers, so the power is the exponent. Of course you can also have negative exponents as well, so if you have 2 to the -1, then 2 to the -1 is the same as 1 upon 2, which is a half, or 2 to the -2 is equivalent to 1 upon 4, which is a quarter, or 2 to the -3 is 1 upon 8, which is 0.125. So if we have negative exponents, we can not only represent our positive values, we can represent we can not only represent whole values, we can represent fractional values as well. So negative exponents allow us to represent fractional values, and positive exponents allow us to represent non-fractional values. So if you note in this box here, we have the exponent, and this is just a copy of this exponent value here. Now if I was to convert this exponent value from the binary to decimal, then this would just be 1, 2, 4, 8, 16, 32, 64, 128. So it'd be a value of 128. And you'll see I've got the value of 128 represented here. Now, we know that if we've got 8 bits, then we're going to have a possible of 256 different values. So the values are going to range from a value of 0 all the way up to 255. Okay, so 0 to 255 is actually 256 values, including the 0. But if we want to represent negative exponents, then we're going to have to say, well, there's a certain fraction of those 256 values that we want to make negative. Now, you've got to work under the assumption they want to make roughly half of them negative and half of them positive. So how do we do that? Say, well, we do that simply by choosing a value called a bias. So the bias value is going to be roughly half of 256. So the bias value that we choose here is 127. So that means that if, say, for example, we had a number in here of 1, ignoring everything else, we have a number in here of 1, that's simply the binary number 1. Well, the binary number 1 would then actually be 1 minus 127, which would be minus 126. So it means that that number is actually minus 126, and that number is minus 125, and minus 124, minus 123, and 22, and so on and so forth. So this bias here allows us to split the exponent range into a positive range and a negative range, so that we can get both whole number values and fractional number values and decimal whenever we do our conversion. So let's go back to our value of 2 here. So we're asking, what is the actual exponent value that is represented by the value, this value here? So 128 minus 127 is a value of 1. So that means that that 1 is the actual exponent that we're interested in. And of course, it's an exponent, but what's the radix? Meaning, what's the base? Well, we're dealing in binary, so we know the base is 2. So we're actually going to have 2 raised to the power of 1. So you can see in the result section here, we've actually got this 2 to the power of 1. So forget about what's in here for the moment. We've already done the sign bit. Now we're doing this little bit here, and this is the exponent bit. So this is 2 to the power of 1. So if I wanted to change that, I could make that 2 to the power of 2. I could make it 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 7, 8. So this allows us to create the positive powers, but of course we can create negative powers as well, because we know if we take this off, then we're going to have a value and put a value of 1 in. This is actually going to be the exponent 1 minus 127, which is minus 126. And this would be the exponent minus 125, minus 124, minus 123, minus 122, minus 121, and 120, and so on and so forth. So we're able to represent both positive and negative exponents. So this allows us to get whole number results and also fractional results. So this number here, 2, is going to be generated by the sign, which is positive. It's going to be generated by this here, so it's 2 to the power of 1. So 2 to the power of 1 is 2. So this is, in this instance here, this is our final answer 2. But we haven't dealt with this thing here. Now this thing here is something called the significand, or as I've called in the course, it's sometimes called the Mantissa. So let's have a look at this little section here in this set of brackets. Now this little section in this set of brackets here is given by all of the green values here. So in this case here, we've got 23 values here, and this is called the significand, or as I call through the course, the Mantissa. Now in this instance you can see the Mantissa is all zeros. So in this point here then, what we're going to have is 1 plus the value of 0. And this 0 here is just the value of all of these. So in this particular example, it's a simple example because the Mantissa is equal to 0. So we're asking, what is the decimal equivalent of this? Well, the decimal equivalent is, well, it's a positive. It's a value of 128 minus the bias, which is a value of 1. So the exponent is a value of 1. So we're going to have 2 to the power of 1 times the value of 1. And the Mantissa is all 0, so we're going to have that times 1 plus 0. 1 plus 0 is just 1. So we're going to have 1 times 2 to the power of 1, which is just 2. So this is our final result, which is a value of 2. So this is a simple example when all of the Mantissa values are equal to 0. So let's have a look and see what happens when the Mantissa value isn't equal to 0. So let's see what happens when we make this Mantissa a value other than 0. Now the way this Mantissa works is that this value here, if I click on it, this is a value of 2 to the minus 1. And you can see this here, I've got 2, and that little hat means the power. Okay, so that's 2 to the minus 1. But 2 to the minus 1 is nothing other than a half. Now the next box here is going to be 2 to the minus 2, which is a quarter. 2 to the minus 3, which is an eighth. 2 to the minus 4, which is a 16th. And so on and so forth, all the way down to 2 to the minus 23. And this is 2 to the minus 23 in decimal here. So let's say we have this one box clicked here. If this one box is clicked, then you'll notice that if you keep your eye on this 0 here, this 0 is going to change because this here is our Mantissa value. So if I click on this, you'll see it changing to 0.5. So this number here that we've now got is the value of a positive value. It's the exponent, which is our 128 minus the 127, which is 1. So our exponent is a value of 1, and we've got a base 2. So it's going to be 2 to the power of 1. And finally, we've got the Mantissa section here, and it's going to be given by 1 plus. Now, this number here will be the Mantissa, and we know that value there is 0.5. So we're now going to have 1 plus 0.5, which is 1.5, times 2 to the power of 1. Well, 2 to the power of 1 is 2, so it's 2 times 0.5. So 2 times a half is going to be a value of 2 times 1.5, sorry, is going to be a value of 3. So this number here gives us the decimal number 3. Of course, we can create a whole load of different numbers here, but you'll notice that whenever we change this Mantissa value, all of the numbers are going to go between the value of 2 and a number that's just a little bit less than 4. So let us just see that. So I'll make it 1 plus 0.75, and you'll see this number increasing, and it will keep increasing, but it will increase by smaller and smaller amounts, because this value here we're adding on is 2 to the minus 6, then 2 to the minus 7, 2 to the minus 8. So if you like, you can think about the exponent as a huge bucket, and that huge bucket is going to contain all of the numbers that we've got between the value of the 2 and the value of a number just less than 4. But if you like, we could say just from 2 to 4. So let's go all the way up here, and we'll add all of these values in, and we can see here that we're going to get a number that's getting closer and closer to 1. We'll never ever quite reach 1, but it gets closer and closer to 1. So now we're going to have 1 plus a number that's very close to 1, so we're getting a number that's very close to 2. Okay, so that's going to be 2 to the power of 1 times, which is 2, times this number here, which is almost 2, so we're getting a number that's almost 4. So that means that when we're in this magic bucket here, which is given by this exponent, we're going to have all of the numbers which are between the values of 2 and 4. But not quite 4, just a little bit less than 4. So if you like, that exponent's going to give us a range of numbers. So that's the exponent bucket for the range from 2 to 4. Now, the next exponent bucket up is going to give us a range from 4 to a value of 8. So let's have a look at that now. So in order to get our 4 to 8, then we're going to have 4 is going to be 2 to the power of 2. So the exponent has to be a value of 2. So how do we get the value of 2? Well, here's a value of 2 here. Because what we've got here now is 129. That's a 129. Minus a 127, which is a value of 2. So we've got that 2 to the power of 2. Now if we take all of the values off of the mantissa here, you can see this steadily getting smaller and smaller. So you can see at this point here, we're going to have 2 to the power of 2, and we'll have 1 plus the mantissa, which is 0. But what we could do is we could put a value in for the mantissa, and we'd have 0.5 again, and we would have 0.75, and so on and so forth. And we can work our way all the way up until we get a number. Again, this number here will be not quite a value of 2, but it will be very close to it. So 1 plus 0.999, so it's almost 2. So really, if we were to simplify this, we could say that we've got 2 to the power of 2, which is 4, times this value of 2, which is a value of 8. So we're going to have a magic bucket of numbers, and all of those numbers are numbers between the value of 4 and 8. Now we could do the same for 8 and 16, 16 and 32, 32 and 64, and we can also do it for the negative number. So we could do it between the numbers a half and a quarter and an eighth and a 16th and a 32nd, and so on and so forth. So we can think about this exponent then as providing a range. So, or if you like, a set of buckets of numbers. And those numbers are going to range, as we just said there, from the 2 to 4, 4 to 8, 8 to 16, and also the fractional values as well. So the exponent tells you which bucket you're in, but the mantissa then tells you whereabouts in that bucket you have to go to, because that bucket, each bucket contains a certain number of values. So the exponent tells you which bucket you're in, and the mantissa tells you whereabouts in that bucket your number is. So another question we can ask is, how many numbers are there in each exponent bucket? Well, we can see here that the number that we're going to get is dependent on the size of the mantissa. You can see the mantissa here, we've got 23 different bits. So those 23 bits are going to give us a combination of zeros and ones, and the combination is going to be 2 to the power of 23. So for example, if we only had one bit in the mantissa, we would only represent 0 and 1, so we would only have 2 possible values. If we had 2 bits, then we could represent the 0, 0, 0, 1, 1, 0 and 1, 1. So we could have 4 possible values, or 2 to the power of the 2 bits. If we had 23 bits, we're going to be able to represent 2 to the 23 numbers. So what is 2 to the 23? So let me get a calculator here and we'll just work that out. So there's a calculator. So we're going to have 2 raised to the power of 23, which is equal to, so we're going to have 800, what's that, 83,000. So we're going to have 8,388,608. So 8,388,608 numbers that we're going to have in each exponent bucket. And we're not going to have any more than that. So this is an interesting thing, because this means that between the first bucket, 2 and 4, we're going to have that 8 million values. Between the bucket 4 and 8, we're going to have 8 million values. Between the bucket 8 and 16, we're going to have our 8 million values. and 16 and 32, we're going to have 8 million values. So you can see that the exponent range is going to increase each time. So the between 2 and 4 is a much narrower range than, say, 16 to 32, but you're still going to have just the same 8 million numbers in each of them. So it means that whenever you are in a low exponent range, meaning a low value, say between 2 and 4, you're going to have a high precision because you're going to have 8 million values in that small range. But if you head up further and further out, so for example in the range 1024 to 2048, so you're going to have the 2048 minus the 1024, which is 1024, and you're going to have the 8 million spread over that wider range. So we're going to have a greater precision whenever we're at a low exponent range, meaning say 2 to the power of 1 and 2 to the power of 2 will have greater precision than say 2 to the 125 and 2 to the 126. So just to conclude now, remember our exponent provides a range and our mantissa provides a precision within that range. Or more intuitively, the exponent provides a box and then another box and another box, and each of those boxes are from 2 to 4, 4 to 8, 8 to 16, so on and so forth. And the mantissa provides a set of numbers that exist within those boxes. But that set of number is a fixed set. And as we go further up the number line, we lose precision because we're widening the exponent range, but we're keeping the number of mantissa values or precision values at a fixed number. So that's provided you with a brief introduction to floating point numbers and how to convert from binary to the decimal, and an intuition as to what floating point numbers are and how they work. Now if you need any more details, then we do have the first course there, and I suggest that you go and complete the first course if you are still new to floating point numbers. Alternatively, you can just continue and you can work your way through it and understand it as we go along. So thank you for listening. I'll get you on the next video. Goodbye.